Good evening, everyone. Myself, Vasudha Sharma, and I will be your NPTEL TA for the course Metal Mediated Synthesis 1, Part 1. And this course is being taught by Professor Deepamrita Maiti from Department of Chemistry, IIT Bombay. So I'll be assisting in giving you all the basic concepts of whatever the course has been studied in weekly sessions, and provided that we will be discussing certain problems and having an open interactions wherever you're feeling any issues or any concepts that you are finding it difficult to comprehend. So we will wait for a few more minutes for others to join and then we can start with the session. Thank you for joining. Okay, so we can start the session. I hope you guys have gone through the lectures that has been covered in week 1. So based on that only, I'll be discussing the same concepts here. And after that, if you have any questions or doubts that you are open to ask. So, as the course title suggests, that we are going to talk about the metal mediated synthesis. There are many different types of catalysts, and specifically when we are talking about the metal mediated, that means we'll be focused on the catalysts which are homogeneous catalysts and they are surrounded about the metal centers, mostly the 3D centers, 3D, 4D, or 5D, like transition metals. So, the first topic or the lecture one that has been covered, it talks about the asymmetric hydrogenation. So we'll go as per the flow of the lectures being covered. So asymmetric hydrogenation, if you see this term, this can be split into two parts. One is asymmetric and other is hydrogenation. Hydrogenation, you can consider that if you have any molecule which is unsaturated, meaning that it has a tendency to occupy another hydrogen over there. So if you are taking an alkene and if I am hydrogenating it using a hydrogen source, it will turn into a saturated compound, which would be alkane, and that alkane can't be further reduced. And asymmetry be related with the chirality, meaning generating the center where it is having all the groups different. Say, for example, if you have a carbon and we know that it has a tetrahedral coordination, so it would be surrounded by, this is your carbon center, and this would be surrounded by all the four different groups. That's what make it a chiral center, and that generates the asymmetry. And when we combine the two terms, that is asymmetric hydrogenation, meaning we are employing some chirality in the system, and that would end up giving you a product which is chiral. So before going into the asymmetric hydrogenation, we need to see what is hydrogenation and which hydrogenation we are basically talking about. So we are basically focusing on the alkene or olefin hydrogenation in this lecture. We know that this would convert to your alkane. Now, if you want to involve chirality into that one, that would turn out to be a asymmetric olefin hydrogenation. Now, carrying out these hydrogenations, we require catalyst system. Catalyst is something, this is a species you can consider, which will provide an alternative pathway having less activation energy. So these are just the basic definitions which I am giving you in brief. For example, if you have a substrate A, which we are considering in this case as alkene, and substrate B, which is your alkane. Since it is lesser in energy, that means the product is stable compared to the substrate. Now I have to go from this step to this step. So it is taking this long energy. If you can consider this is your energy bar, and here it is taking a long energy, a very high amount of energy to convert into the desired product. And if I am involving my catalyst, now it will go through a very shorter path and comes over here. It would be having some energy, but it would be a catalytic path, and the energy that is being required, that compensation would be very, very less compared to the non-catalytic path. So that's where we need a catalyst to carry out these kind of hydrogenation reactions. That's why they're called as catalytic reactions as well. Now moving to the catalyst that we are interested here is the shock Osborne catalyst. So this is basically a rhodium-based catalyst, and majorly it has phosphine as groups or ligands, you can say, which are coordinated to the rhodium. So how this transformation, if I am considering that this is my olefin, this is a seven-membered bridged system, and if I need to convert it into a saturated alkane, a cyclic alkane, I need this rhodium catalyst. So how this mechanism will work and how it will convert your olefin into the alkane. So let's see. Generally, it's an active system. If you can consider, it would be phosphine and phosphine. You can consider it as either they are coordinated to each other or they are simply PPH3. Generally, they are a bidentate system where they are coordinated with certain ligands. Say, for example, if I have phosphorus here and something like that, and this is having PPH2, and now it is coordinating with your ruthenium. So this is somewhere the marking, that hemicircle that I'm making, that is implying that these two are connected to each other. Okay. So now if we say that rhodium is connected to this one and it is having on the other side some solvent molecules, they will leave and they will form an active 12 electron species. This is your active catalyst, which is going to participate in the hydrogenation of the olefin. How it will work? So take your first active catalyst, the rhodium. Now, since we are talking about the olefin hydrogenation, the first step is the olefin coordination over here. So olefin will come and coordinate with your rhodium since it's electron deficient. So the pi electrons on the olefin can coordinate with the rhodium. So here the interaction would be like this way and phosphorus will remain as such. Now the 2 electrons are coming from olefin. So it will increase from the 12 electron to 14 electron species now, having a charge outside. Now moving ahead, what we have to do over here is firstly it will interact with the hydrogen and that would cause it to be an oxidative addition. So oxidative addition is basically something where if I have H and H or H and X, so one this bond will break and one will connect to rhodium this side and the other part is also going to connect over here, increasing the oxidation state by +2 because it is going to donate the 2 electrons to this species and itself reduce, leaving out the 2 electrons. So therefore, what it will do, it will form this P and P will remain same. Rhodium is here, the coordination with olefin, and one hydrogen will go here, another will go here. Now at this point, since we have this kind of olefin, it can transfer the electron, one hydrogen can go and transfer to this position since rhodium is connected to alpha and this is beta, and therefore when transfer of hydrogen can happen, so it will ultimately be forming H over here. Now if you'll see, already our olefin has been converted to an alkane species and it has to regenerate the catalyst. So what it will do, if the oxidative addition has happened, it would definitely undergo the reductive elimination, meaning this species is now going to really take more electrons or 2 electrons from the substrates over here. And these both of them who are cis to each other, they will leave as your alkane. This is your alkane, which is your desired product. And this is your active catalyst, which was being used and regenerated again. So this is how the shock carbene, this is how this orthon catalyst, which is a rhodium-based catalyst, it helps in doing the olefination. First, olefin gets coordinated, then hydrogen gets splitted using oxidative addition. After that, there is a insertion of that hydrogen to the olefin side, making it an alkane. And for releasing the product, it will undergo the reductive elimination and regenerating your active catalyst. So as I mentioned in my first slide that we are interested in having an asymmetric hydrogenation, this can only be possible when you are having either you can make your catalyst as a pre-catalyst and then you're involving some substrate and then you can induce a chirality, or the catalyst that you are using, it is already having a chiral center, which can induce a chirality into your product. And here, if you carefully see, the only way that we can have a chirality is your phosphine system. So we can make the phosphine ligands as chiral so that it can induce the chirality into your system. So the phosphine ligand in the shock Osborne catalyst can be made as chiral, or we can use chiral substituents based on that, and this can lead to asymmetric hydrogenation of olefins to corresponding product. So basically, why are we interested in asymmetric hydrogenation? If you see many pharmaceutical medicines that we see nowadays, they actually have, most of them are having a chiral synthesis because they are selective towards certain properties. So in that regard, if we are very application oriented, we need to design the catalyst in such a way that it would serve the purpose. That's why this course is all about the metal mediated synthesis. So we need to design, we need to synthesize the catalyst in such a way that it would give us a product which is of our major interest. So instead, earlier I had used simple phosphine. If you can consider a phosphine, which I showed you an example, if you can consider this example, and here I am having a CH2 and CH2, pH3. Earlier it was PPH and PPH. You can consider that way. So this is a system where if you'll see, the two groups are similar, so it is not a chiral center, it's a non-chiral center. Or we can say it's a non-chiral ligand. What if I change one of these groups into something else? Say, for example, now I have the skeleton is same, like CH2 is binding to two phosphorus centers. One pH, another pH is same. Here I am having AR group, where AR is another type of, you can consider a phenyl group with NH2, say for example. So I'm denoting AR as that. And this actually generates a stereo center. Now it is showing it is above the plane, and the other side we can have an AR which is below the plane. And when it is above and below the plane, even if you have a mirror plane, it is not going to give you any reflection over there, because one is above the plane and other is uh, below the plane. So this makes it a chiral center, or this can be other way around. You can have an AR dash also here, where now AR dash is something which is like OH group or any other group. You can have methyl group also there. So this center, this phosphine based system, now this ligand is your chiral ligand. And at this point of time, when we have a chiral ligand, AR, pH, AR dash, pH, now when this phosphorus is going to coordinate with your rhodium, which is your 12 electron active species, and when it participates in converting the substrate. Now I'm taking a substrate which is, say for example, PH, there's a phenyl group and there's a double bond having an NH and a mild center and acid center. Now our interest is to convert this double bond into a single bond using this catalyst. So since we are using a chiral system, it will end up giving us phenyl group. Sorry, this is your acid group is going to be not going to be affected because it's a functional group tolerance. Similarly, your NH group, OMe, they are not going to reduce under this condition. So at this point of time, as we said, if it would have been another case where actually this course, I am here to help you with the basic concepts. So I have to cover the basic concepts and the assignments that I will be giving you. If you have any question, you can put your question in the chat box and then I'll look into it, because those assignments I'm not allowed to discuss in this platform. You can ask me the question which I am teaching you right now, and if you have any doubt, and if it is related to the assignment, because I have to give you my own assignment. So if that is okay with you, you can put your question in the chat box and I can answer you in there. Let us first finish the concepts that we are starting, because other students are here for first learning and then problem solving. Okay, so what I was talking about is that we are having a phosphorus group over here. And this phosphine is basically, if I'm not having a chiral center over here, this would end up giving me a normal alkane and having a hydrogen over there. But since I'm using, just a second. Sorry, I didn't understand your question. Can you please unmute yourself and ask the question? Hello? So I'll just clear some doubts over here. This platform, here I'm going to first teach you the basic concepts that has been covered in the lectures so that you can ask me the questions regarding the lectures directly. Secondly, if you have any query regarding the assignments, I will not be able to answer the questions of the assignments until unless that assignment is being finished, because the answers would be revealed later. And that questions you can ask directly onto the NPTEL forum. The questions that we will be having over here, you can ask me at any point of time, and the query also. So that won't be a problem. But if you're asking for the answers or the full explanation of the assignment questions, that I'm not allowed to do that, because those answers would be revealed to other students later. So once that has been covered, maybe in the next week, once this is over, then I can, if you have any doubt, and then we can interact on that. So your question, Nas, that we only have to attend the lecture and do the assignment for nothing else. I didn't understand this question. Can you please explain it? You can also type in the chat box to make it more clearer. Okay, if there is no question, we can move ahead. So as we were discussing that now, since the chirality is there, we are going to see a chiral center generated at this position, because one side it is going to have a hydrogen, other side it is going to attach with nitrogen. And if you see at this particular center, all the groups like COH and NH group, and other side this, and one side there would be H. So all the groups are different, therefore it has become an asymmetric hydrogenation. Okay. Now, since when we are talking about the asymmetric hydrogenation, we always get two types of isomers. The isomers that we see in asymmetric hydrogenation is generally the R isomer or the S isomer. So these are basically both the mirror images of each other. So if I have this example where I have the substrate, the double bond O, here the acid group is there, and again there is an amide group. So this is your substrate, and this has to be performed an olefin hydrogenation. Now here, if you'll see, we will be having two types of products using the catalyst, the star catalyst, which is your chiral catalyst that we are using. Now we can expect here the two products. One is COOH, pH, hydrogen is here, and NHWONE, right? And this is your S isomer, which has been formed as a major product. Now, if I take a mirror image of this one, it would give me OMe, there's the one. So this is Me, NH, pH, COH, H. So this is your R isomer, which is minor. When we looked into the kinetics and the mechanism of this one, we didn't find any way that S isomer could be the major product of this particular reaction. So how it has turned out as major product? So for this one, we need to understand we have a curtain Hammett principle. So in this principle, what we mean to say that if we have a substrate which are isomers or in equilibrium with each other, say A and B, so whenever we consider, so these are the substrate, and if we consider the energy profile of this one, so here we have here we have a substrate A, which is going to transition state at TS1 and giving a product B, right? So we need to make it put down. Because it is stable. And other side also we have a substrate B, which is lesser in energy, but the transition state is higher in energy, and the product D is stable, D. So these two are in equilibrium. So what really happens is, here we can say that though A is having higher energy, but the product formation intermediate can be characterized in case of A as the transition state 1 is less in energy than transition state 2, which is of B. So it doesn't matter whether the energies of A and B are higher or less. It totally depends upon the transition states if they are in equilibrium. So the transition state energy for A going to C is lesser. That means this can be characterized and this would be able to form. This has happened for the case of S isomer. Even though S isomer route is not feasible, this is not being formed, but that has turned out to be a major product. Even the possibility is not favorable as case of the A. So this can be easily explained using the Curtin-Hammett principle. Moving ahead to our lecture 2, which was regarding the transition metal carbines. In this case, we generally have a classification into two. One is your Fischer carbine, and another one is your Stock carbene. Let's discuss one by one. So firstly, we have Fischer carbene. This is basically if you are, this is having, we can take an example where we have a chromium. It is connected to carbonyl group and a carbene is there which is connected to methoxy group and a phenyl group. So basically, we can understand that in Fischer carbene, and there is Stock carbene, the difference we can talk about. So the first difference here is, here the chromium is associated with pi acceptors ligand. That means the metal center needs to be in low oxidation state, having more density. So here the metal is either late or middle transition and low oxidation state, generally 0 or +1. Here the carbon center of the carbene is electrophilic in nature and it is connected with, has pi donors, say for example, OR, NR2, etc. So this is the basic structural description of your Fischer carbene. For Frock carbene, we have an example where we can describe here itself. For chalk carbene, it is neopentyl tantalum carbene and tertiary butyl, and there is H. Considering that here the metal center is early transition metals. They are generally in high oxidation state. So this part of meeting will end in 10 minutes. So kindly rejoin the same link. Thank you. High oxidation state of the metal. And so these are electrophilic and generally connected to non-pi acceptor ligands, as we have seen the nucleotide. Whereas the carbon center of the carbene, that is nucleophilic in nature, and it is not connected, it is connected with non-pi donors. For example, methyl, tertiary butyl, hydrogen, etc. So this is the basic difference of the Fischer carbene and the Schoch carbene, where the metal center would be in, where the metal center of the Fischer carbene is nucleophilic in nature, and based on that, it is having more electron density, so it is stabilized by having the pi acceptor ligands. Whereas in Schoch carbene, your metal center is highly deficient, so it is not having any pi acceptors, only the neopentyl butyl groups are there. The carbon center of the carbene in Fischer carbene, it is electrophilic in nature, and to make it stabilize more, it is being connected to the pi donor over there. Whereas in the Schoch carbene, it is nucleophilic in nature. So the trends are totally different. In Fischer carbene, the metals that we see generally is the chromium, tungsten, molybdenum, where they would be stabilized and they would be having low, they can stabilize in low oxidation state, whereas in Schoch carbene, we generally have the tantalum, titanium, where they would be in higher oxidation state. So let's see the synthesis first of the Fischer carbene. And if there is any doubt, please let me know in the chat box or you can unmute yourself. Okay, so the Fischer carbene that we have, So if we are talking or if we are targeting, we can take a simple or general example, not specifying it. So we are going to talk about the metal carbonate, where M can be chromium, it can be molybdenum, it can be tungsten. So you can make any kind of Fischer carbon if you know the synthetic process. So here, this can also be written as 5 carbonyls here, another one here, just to make a bit clarification. So when we are using our lithium, so what it would do, it would insert the R into the carbonyl group, and therefore it would form as M double bond O, CO, and R. So what it is going to do, and this would create a minus charge on metal center, and lithium anyway, the positive outside. Now when you treat it with a diazomethane, so it will introduce the CO5 metal double bond. That CH2 group will get introduced, and OMe, and this R group is here. So this CH2, N2, this will go and get stabilized on this one, and there could be a double bond over here. And this would give you a shock Fischer carbene. One such example already we have seen. The other part that we have is the shock carbene, which has been accidentally found. So Shock wanted to react the neopentyl tantalum chloride with 2 lithium neopentyl and was expected that it would form a neopentyl tantalum, but got neopentyl tantalum carbene contributide. So also another examples of these shock carbenes are CP2 titanium double one CH2, Tebbe's reagent CP2 titanium, CH2 aluminium, chlorine, methyl and methyl. So this is your Tebbe's reagent whose applications are many that we will be discussing in sooner point of time. Now there is another set of catalysts which has generated with the combination of shock catalyst, and that category is your very important Grubbs catalyst. And in this Grubbs catalyst, so this is also a type of a shock catalyst. If we see the structure of the Grubbs catalyst, it is a 5-coordinated, a ruthenium-based system where we have a PCY3 and double bonded. This carbene is also a nucleophilic center. That's why it makes it a shock-based system. Now, Crafts catalyst is also having a lot of applications. If we consider the shock one, they are used in olefin metathesis, they are used in carbonyl olefination, and these certain descriptions of the reactions that we are going to talk about. The first one is the metathesis. So applications are, one is olefin metathesis, and the other one is carbonyl olefination. So let's take the first one, olefin metathesis. So what really happens is like when we have a CC bond formation, considering that we have one type of alkene over here, which is R, and another type of alkene is there, which is this one. Now, when we are using a Grubbs catalyst, which is a carbene-based system, and this is reversible also, what really happens is this part and this part gets coordinated and to make a new catalyst. So this becomes an R and R dash. Another part is also like R and R dash. So we get two molecules of R and R dash. A new olefin is being generated. So this is where the new CC bond has been formed, and this is known as an olefin metathesis. Similarly, the other type that we have is olefin carbonyl. Sorry, it's a carbonyl olefination. It's a carbonyl olefination. So basically, if I'm having a carbonyl group, which is this one, where X can be anything, and I'm treating it with a catalyst, this Scrubs catalyst. Now what will happen? Now this is one type of, you can consider it as a one type of olefin, another type of olefin. Now it will tend to form, you can consider that instead of this uh, X part, that R dash part has come, and this M and this oxygen will now form a metal oxide, which is quite stable metal oxide. So this is what we call as a carbonyl olefination, where also a new bond is being formed between two different centers, but the difference is one is olefin, another one is carbon. Now we have different types of olefin metathesis reaction. Which is one is your ring closing metathesis, which means that bond formation is happening for sure between two different olefins, but it is a closing mechanism. So if I am having a ring which is like this way, this ring, this particular part shows like it is having a long chain. So you're not going into that one. It can be any number of chain, CH2 and CH2s. So if I'm taking a catalyst and symbolizing it as a M11, which is the metal carbon, and in the forward direction, it is more feasible. That's why the arrow is more towards the forward direction. Now, if you see here, this part and this part, this can form a double bond, a one part of the olefin, and the